So neutron stars are dead. Core of a giant star exceeds the Chandrasekhar limit. It collapses, massive explosion. You have a dead star. The final thing of the star's life as it's dying is this giant supernova explosion. You have this big expanding cloud of gas, and the corpse of that star, the dead thing that's left, is the neutron star. Now, we can sort of talk a little bit about life after death for the neutron star because you can still see its existence through the pulsars. And as they rotate, these flashes of light and so forth. And so that's, I mean, but still, it's pretty much a dead object you're seeing. So now we want to talk about zombie neutron stars. Yeah, okay. So, that's like life after death after death. Okay, so we have the death of the star, and then the neutron star is dead, but they can still do stuff, and that's kind of an interesting thing is they can still do stuff because they're in the universe. So one thing that can happen is that you can have a neutron star near another star. Now a supernova is a massive, horrendous, giant explosion, but stars are actually tough. So in a binary system, sometimes the companion star can survive, and then when it dies and fills its Roche lobe, it can dump stuff onto the neutron star. Well, all the stuff dumping onto the neutron star is going to swirl up and make an accretion disk. The accretion disk is going to be compressing. It's going to get hot. It's going to start a fusion in the accretion disk. So now instead of fusion inside of a star, the fusion is in the accretion disk. And then as this blob of fusion goes around, it will brighten up and dim down if you're out here looking at it. And then you're going to have going faster and faster and faster, generating magnetic fields. You get beams of radiation coming out. If those beams happen to swing past you, you get a flash of high energy radiation or X-rays. And so you get these flashing X-rays, X-ray bursts on a regular basis. Well, the other thing that can sometimes happen, you get these flashing X-ray bursts as it's going by, and so they didn't know what these were at first, and so they launched several satellites outside the Earth's atmosphere to study this. X-ray Timing Explorer is one of the first ones dedicated to just studying those X-ray bursts. Well, the other thing that sometimes happens is that with this huge magnetic field, you can get a weak connection event similar to a solar flare, except it's a flare on a dead star, on a neutron star. And if that happens, you get an incredible, huge blast of radiation that comes out. And so you have these massive X-ray bursts. Well, what they discovered was sometimes there were actually even bigger X-ray bursts than just the massive ones, because some of these stars, as stuff is spiraling into them. Remember the previous slide where we had the stuff spiraling into there, or two slides ago we had the dying star and spiraling stuff into the neutron star. Um, what can happen there is that all this stuff spiraling in can make the neutron star rotate faster and faster and faster. The faster and faster and faster the neutron star rotates, then what's going to happen is that it's going to end up speeding up, increasing the magnetic field until it's such a powerful magnetic field that it's even more furiously more powerful and more intense than the incredibly intense magnetic field of a regular neutron star. At which point, this thing is the most powerful magnetic fields in the universe, and we'll call it a magnetar. A reconnection event in a magnetar can create a massive blast of radiation. In fact, one of these magnetar events from thousands of light years away, a number of years ago, 1998, was so powerful. This is a satellite record of the event right here. Was so powerful it actually ionized the Earth's upper atmosphere and blocked radio communication with satellites for a while from thousands of light years away. That gives you an idea of just how powerful of an X-ray burst that this is. Good news is, down deep in the atmosphere, we were protected from it. Okay, so the more powerful magnetic field gives rise to a magnetar. and they can spin in a fraction of a second, sometimes up to 200 revolutions per second. So they spin in milliseconds. And so we sometimes call these millisecond pulsars or millisecond neutron stars or a magnetar. Number of high energy satellites have been launched to study magnetars and magnetar. A number of magnetars have been found. Most of them in our own galaxy. Really massive stars don't live very long, so they're normally found in places where stars are actually actively forming. They're forming in the plane of the galaxy. So this is kind of a map of the sky here with our galaxy across the middle there. And most of the magnetars are located along the galaxy with one exception, and that's located in a little small satellite galaxy that orbits around the rest of our galaxy, something called the Large Magellanic Cloud. So, as magnetars age, because they've got all this high strength magnetic field, charged particles swinging around, giving off radiation, we'll call synchrotron radiation. But that energy going away from it, robs the magnetar of its rotation, so it slows down. The top graph here shows the period increasing. Period is how long it takes to rotate, so a longer period means rotating slower. As it rotates slower, this blast of X-rays and gamma rays from the magnetic reconnection drops off. And so you end up with a magnetar, which is a young sort of thing. And then as it rotates, it gets less and less active, and eventually just becomes an X-ray pulsar, and then finally a dead magnetar, which is an ordinary neutron star. One other interesting thing here is that as the signals go through space, you can actually measure the interstar medium by using pulsars, because different frequencies travel at different speeds. And this is a famous effect in glass. It's called dispersion. Different colors of light travel at different speed through glass. That's why prisms bend different colors of light differently. But the same thing happens in space. So you can actually have a graph here of a pulsar and different radio waves going at different speeds, and some of them go a little bit faster, and so the pulses arrive early. Some pulses arrive a fraction of a second later, and so by measuring the slope of that graph, you can measure the density of the interstar medium between us and the pulsar. Stephen Thorset, astronomer, 1993, noticed that a pulsar was wobbling as if there was some small object orbiting it, and realized the small object was about the mass of the Earth. Well, that's way too small to be anything other than a planet. So he announces that this pulsar has a planet. Now, ironically, this is actually discovered right before regular planets or other stars were discovered. This may not be weird. This may not a normal planet because it's orbiting a neutron star, which is not bright. It just gives off lots of radiation, so it's going to be a frozen planet bathed in hard radiation. So that's going to be kind of weird. There are some other incidences here where pulsars seem to have planets orbiting them. In some cases, they may grab the planets from but again, 1990s, another planet discovered, and eventually multiple planets discovered. And so the idea would be that possibly what's happening is that when you get a supernova, you blow all this stuff into space, and then some of the stuff hangs around and forms like a new proplyd around where the pulsar is, around the neutron star, which has lots of gravity. And so this new proplyd produces brand new planets. Now, these are not normal planets because they are formed around a dead star. They're not likely to have the same kind of composition as planets forming around a brand new star because they were formed out of supernova debris. Several of these pulsars have been discovered to have disks around them or planets. And so this suggests that very possibly that the debris from a supernova might frequently, or at least occasionally, form planets around a pulsar. So pulsar planets are probably not as rare as we might think they are, but they are much likely to be made of heavy. Remember to get all this nuclear fusion that makes all kind of other things in a supernova. Well, what if we had two neutron stars near each other? Two big stars died. They each left a neutron star. As the neutron stars orbit each other, they give off gravitational energy and eventually they merge. When they merge, you can get a sudden giant blast of radiation, but it would also tend to cause another collapse. We'll talk about what that does later, but it would release so much energy it would fuse a whole bunch of other things that normally would not be fused even in a super. And so what would happen is you start making the rest of the periodic table. A graduate student by the name of Jennifer Johnson a number of years ago at Oklahoma State had worked out a periodic table of elements that NASA published showing the origin of different kinds of elements. Some that left over from the very beginning of the universe, that's in blue, the Big Bang stuff, and then dying low mass stars doing nuclear fusion that produces the lithium, carbon, and so forth. And then some of these other things, exploding massive stars, that makes all the stuff in yellow right there. And then merging neutron stars, this burst of nuclear fusion making a bunch of other things. And so the whole periodic table is built in this kind of fashion. Some of these other things down here are also made when a supernova, when stars explode, but a large portion of it is made by merging neutron stars. But a neutron star can only be so big itself. So theoretically, if a neutron star gets bigger than 3 solar masses, then the neutrons themselves break down and it collapses further. And so that's going to be our next topic, is what happens if you collapse beyond a neutron star.